Hello everyone, my name is Sajad Khodadadian, and today I'm going to present you my work Finite Sample Analysis of Two-Timescale Natural Actor Critic Algorithm. This is a joint work with Dr. Thinh Doan, my advisor Professor Siva Maguluri, and Professor Justin Romberg. First, I'm going to explain to you the notion of value function. In an MTP setting, we have a set of states and actions. We first sample the first state S0 from a distribution row, which I'm not going to show during this presentation. And then at each time step, you use the policy pi and sample an action AT according to the policy pi, and having this action AT, you move to a new state ST plus 1 using the transition probability P. After this transition, you receive a reward which is denoted by R, ST, and AT. We also define discount factor gamma, which is a number between 0 and 1. We can further define the Q function as follows. QP is just a value function, except that I condition on the first state and action. Our goal is to find the optimal policy which maximizes the VPi function. One of the methods which you can solve the above problem is to follow a gradient ascent method. We can think of VPi as a function which inputs the policy P and outputs the value function VPi, and you can keep on following the direction of the gradient, and since the pi is in a bounded set, you have to project back every time you update the policy. However, the problem is that VPi is not a concave function, and we do not know the gradient of VPi. So in this problem, we cannot use any of the results of concave optimization. In order to deal with these two problems, first I introduced natural policy gradient. Assume I parameterize my policy with a vector of parameters theta in a softmax manner, as is written here. First, assume I again use the gradient ascent, this time with the new parameterization theta. So I just keep on updating my theta with the gradients of the value function taken with respect to the theta. However, if you just simply use the gradient, you keep on jumping around and your convergence rate is very slow. An idea to improve the rate of convergence is to precondition the gradient. The preconditioning is just multiplication of the gradient with some matrix, and if we can choose this preconditioner properly, we can hope for an improved rate of convergence. There are two famous preconditioners. One is the Hessian matrix, which results in the Newton method, and the second one is the Fisher information. The Fisher information preconditioner results in natural policy gradient method. Furthermore, the corresponding updates of the policies is simply just multiplication with an exponential and division with the normalizer. The good news is that if we keep on following these updates, one can show that the corresponding value functions converges with the desired rate of 1 over k to the optimal value function. Note that in this result, we assume that the step sizes beta k are kept constant. So, in order to implement natural policy gradient, we need to run a loop. In the first step of the loop, I calculate the Q function, Q pi k, and then I update the policy using the update which is written here. However, the problem is that I usually don't have access to qpyk. So one way to solve this problem is to run an inner loop and run this inner loop for infinite number of times, and during this inner loop I keep on sample a trajectory from the policy pk and update a Q table with what is written here. It can be shown that this inner loop converges to the qpyk after infinite number of updates, assuming that we have enough exploration. However, an infinite loop is impossible in practice, so one way to deal with this problem is to just simply remove the infinite loop and update the Q table one time only. And we can further update the policy with the corresponding Q function qk. This loop has two separate stages. The first stage is called critic, the second stage is called actor. And this whole algorithm is called two-timescale natural actor critic. Note that since I'm removing the infinite loop, I have to somehow account for that. In order to do that, I can choose step size at beta k much smaller than alpha k. And once I run this loop, the actor moves slower than critic, and it can be interpreted that each step of the critic corresponds to several steps of the actor, so that somehow you account for this infinite loop. However, the important question is that does this algorithm converges, and if it converges, with what rate it is going to converge? Our main result shows that if you choose the step sizes alpha k and beta k as 1 over k to the power 0.5 and 1 over k to the power 0.75, and assuming sufficient exploration of this algorithm, for k large enough, the expectation of the corresponding value functions converges to the global optimal with rate 1 over k to the power 0.25. There are several challenges in this analysis. First of all, the intervened difficulties of having updates at 2 timescales. Second, the asynchronous nature of the Q table update and the Markovian randomness. Regarding the assumption, if you follow the trajectory generated by the actor critic, you keep visiting different states and actions. Suppose I denote the number of visits to a state and action S and A in a time frame L with tau S and A, and calculate the minimum number of these taus, minimum over S and A, and calculate the probability of these minimums to be equal to 0. Call it P1 for the frame 1, P2 for the frame 2, and so on and so forth. Our assumption asserts that the supremum over all these probabilities should be strictly less than 1. Thank you for your attention.